All right. Okay, so we have that now. Well, let's go to the graph. I mean, the graph I probably should have put before all this. Although really, I guess I didn't have to because I already said before I did this example that any non-vertical line, the graph of it passes the vertical line test, right? As I have here. So this does give us y as a function of x, even before the graph. I mean, here's the graph, but you can also see I just put some points on here, on the right side here, just to illustrate what I'm saying. Namely, 3, 0 is on the graph, right? So from the graph, we can get input and output. Namely, since 3, 0 is on the line, right? This is telling us that the function takes 3 and sends it to 0. F of 3 goes to 0. Or if you want another example, notice that 4, 2 is on the line, right? You go to 4, go up, and you can see we went up 2 units. So this point over here is 4, 2, okay? So f of 4 has to be 2, as we can see. Let me just fix that. So f of 4 is equal to 2. So that's what f of 4. So that's what we have here. Okay, good. All right, so that's what we have here. So again, you can also read the input and output from the graph as well. Okay. Here's another example. Here we have this line, which is very similar actually to the other example. We have 4 times x minus y equal to 1. Okay. Right, but again, the graph of this is a non-vertical line. How do I know it's not vertical? Because vertical lines don't have the y variable there. Okay? They don't have the y variable there. And so because of that, this is a non-vertical line. Right? Remember, if you have ax plus b times y equals 1, although I guess instead of plus, we have a minus here. But remember, subtraction is the same as adding the negative. So since it's in this form, we know the graph of it is a line. So we know right away that this does give y as a function of x. And here we're solving for y in terms of x, right? Doing so, we get y is 4 times x minus 1. And so now we have y as a function of x. Namely, if I let f be this function, we have f of x is 4x minus 1. So again, I'm replacing y with f of x. That's what I'm trying to do here. Okay? That's what I'm trying to do here. So from here, we can actually get, for each input, we can get our output. That's what this is saying. So for instance, if we do, let me do this quickly. For instance, if we take 0 as our input, what would f of 0 be? Well, if you put in 0 into this as our x, right? This is saying, bear with me, I can't draw this way. I can't draw at all, actually. But if we do 4 times 0, right? Minus 1, what do we get? We end up with negative 1. Okay, that's what we get here. So in other words, what this is saying is f of 0, right, is negative 1. Okay, we have f of 0 is negative 1. And you could do this for any x, actually. I mean, if you were to graph the function, which you can do, it's not hard to graph, it's a line, right? You can easily get all the function values as well. I don't know if I can really fit in another, let's see, I'm running out of room here. All right, hopefully you get this. I mean, darn, I'm out of space. Here, let me try drawing it over here. I mean, in general, you have x, remember, going to f of x. We have our formula for f of x. Now that's what we have here. So we have 0 to f of 0. Let me see if I can do another one. I really don't have room. Let me try one more with 1. I really want to make sure everyone understands this. So we have 1, for instance, that's our input. Okay. You put 1 into the function for x. You get 4 times 1, which is f of 1. Bear with me. You get, that's equal to 4 times 1 minus 1. What is that? That's equal to 4 minus 1, which is 3. So f of 1, in other words, is 3. Okay. I really hope that makes sense what I just did. Okay. Here's another example. X times y equals 1. Okay. Now from here, we want to see, does this define a function? Y is a function of x. So again, as I wrote here, we get y in terms of x. So you want y equal to something. So we have y equals 1 over x. So basically, we just divide both sides by x, and we get this. So if I call our function f, again, replacing y with f of x, we get f of x is 1 over x. And I don't know if I showed you the graph of this, but this is what the graph looks like. Now, how do I know this? Actually, I don't know if I said that, but how do we know that the graph of this is, how do we know this defines y as a function of x? The graph of it here, it does pass the vertical line test. Okay, I probably should have said that before I did this, but I guess it's really, well, but anyway, it does define y as a function of x. Again, the graph here does pass the vertical line test. So this is the graph of y equals 1 over x, which again is the same thing as this. Okay. Okay. It does pass the vertical line test. I know as you get further out here, it's easy to see, but as you get closer to the, what do you call it, the y-axis, couldn't think of the word, it looks like it doesn't, but it actually does pass the vertical line test. I mean, the book also goes into how to determine if an equation defines y as a function of x without a graph, but I tried doing that before. It gets really kind of complicated, so that's why I'm using the graph idea. All right. Okay. Yeah, let me just okay, let me just do this. Okay. Okay. I mean, I know we haven't like done, well, we did some examples today, but I really want to make sure we do examples of this next week, which I'm planning to give like a worksheet, not like a worksheet, but I'm trying to post some examples. You'll see what I mean, because I want everyone to really try this though. Okay, some people responded, some people didn't. I mean, I really want to make sure everyone's understanding this. All right. All right. Okay, I guess we'll keep going then. So, all right, let's keep going. So remember how from a relation we had the notion of a domain? Okay, well, in general, you can get the domain of a function. Okay? You know, we got it from the relation. Again, it was in the definition. It's just all possible inputs that go into the function. Right? That's what the domain of any function is. Okay, it's just all the possible inputs. Now, what the book does, and I'm doing this, if you have an equation, it's always the largest set of numbers that you can plug into the formula, you know, to the equation, and get a reasonable output. Essentially, with an equation at least, I'll go into how to get it from the graph. That could be a little bit tricky. But from an equation, you basically follow these rules when you're looking for the domain. I mean, the range gets even trickier, but we're not going to do that. So for the domain of a function, to get the domain from an equation, basically you have to find all numbers that you can plug into x and get an output that makes sense. And another nicer way of saying that is you just want to follow these rules. You never divide by 0. You know, the denominator has to be non-zero. I do an example down here, but let me just say it though, that if you have 1 over something, You just want to make sure that denominator is never 0. So the domain would be everything such that the denominator is not 0. You never take the square root of a negative. Again, we're not looking at complex numbers, so we don't take the square root of a negative number. And this number 3 generalizes it a bit. Basically, if you have the square root of some expression in x, you just want to make sure that expression is positive. Excuse me, sorry, I messed up. We'll do an example shortly, hopefully shortly. But if you have the square root of something in the denominator, then you have to make sure that expression is positive. I know it's not making sense what I'm saying. We will do an example, if not today, then next time. But number 1 here, I'm just illustrating that down here with this example. If you take, for instance, 1 over x, right? Well, we can never have this denominator 0. We can't. And so because of that, the domain would be all numbers except x equals 0. Over here, this is what I'm saying in number 2. You don't take the square root of something negative, okay? So in this case, you want to make sure your x here is non-negative. So in other words, the domain is all numbers such that x here is non-negative. And so from here, we have this interval, in other words, as the domain, okay? That's what the domain is. Okay, so actually we will see an example of number 3. So if you have the square root of something in the denominator, what I'm trying to say in number 3 is you want to make sure the radicand, what you're taking the square root of, is strictly greater than 0 if it's in the denominator, as in this example. So to get the domain of this, we want to make sure that we're taking the square root of, that has to be strictly greater than 0. So in this case, we have 2x minus 4 strictly greater than 0. That's what we want. And that's what I'm basically solving for. So we're using what we saw in 1.5. We want to solve this inequality. And that's what I'm doing here. Remember, what do? You just like an equation, you isolate x, right? So I'm adding 4 to each side, okay? So I get 2x greater than 4. Okay. Then we divide both sides by 2. I'm dividing by a positive. The inequality doesn't change, okay? And we get x is greater than 2, as you can see. So in this case, the domain is all x such that x is greater than 2. And I wrote that as an interval as well, as you can see. So again, that's what I'm trying to say, though. But if you have the square root of something in the denominator, you want to make sure the radicand is strictly greater than 0. Because you can't have 0. So that's what's happening. Okay, this was some other stuff. I'll probably start from here next time. But these are just other functions you're going to run into in math. There's a polynomial function, which essentially is f of x equals a polynomial in x. What's nice about these functions, they're very important. They all have domain, all real numbers. So you could take any number in the world and plug it in for x, any real number, and you'll get an output that makes sense. In other words, the domain is all real numbers. Okay? In particular, if n is 2, what we have is a quadratic function. We're actually going to see how to graph that in chapter 3. It's fun, don't worry. All right, we got to stop. All right, so let me stop recording.